Hi. Hello everyone. Welcome to another anti-relativity talk. Hello and welcome. So, the amazing subject today is about preferred frames. And I think in the last talk, when it was ending up, when we were talking about a twin paradox, sort of like somebody didn't know about what preferred frames were. So, I want to explain what preferred frames are in this little talk, and then we can discuss it. So first of all, I want to present a video showing explaining what frames of reference are, and I think it's quite a good video. Uh, I'm going to only need to show the first 10 minutes of it. It's rather a good talk from the 1960s, and it's kind of trippy as it's advertised. So we can play it now. Have a go for it. There. Can we go? Sound comes a little further on.
We are used to seeing things from a particular point of view, that is, from a particular frame of reference. And things look different to us under different circumstances. At the moment, things look
You look peculiar. You're upside down.
no, you're the one that's upside down.
No, you're upside down.
No, I'm not. He's the one that's upside down, isn't he?
Well, let's toss for it.
All right.
Okay. You lose. He's the one that's really upside down. You better come into my frame of reference now.
My frame of reference was inverted from what it usually is. That view of things would be normal for me if I normally walked on my hands.
This represents a frame of reference. Just three rods stuck together so that each is at right angles to the other two. Now I'm going to move in this direction. You see the frame at the same spot on your screen, but you know I'm moving this way because you see the wall moving this way behind me. But how do you know that I'm not standing still and the wall moving? It was the wall that was moving. Now the wall has disappeared, and you have no way of telling whether I am moving or not. But now you know that I'm moving. The point of this is that all motion is relative. In both cases, I was moving relative to the wall, and the wall was moving relative to me.
All motion is relative, but we tend to think of one thing as being fixed and the other thing as being moving. We usually think of the earth as fixed, and walls are usually fixed to the earth, so perhaps you were surprised the first time when it was the wall that was moving and not Dr. Hume. A frame of reference fixed to the earth is the most common frame of reference in which to observe the motion of other things.
This is the frame of reference that you're used to. The frame is fastened to the table. The table is bolted to the floor is anchored in the building, and the building is firmly attached to the earth. Of course, the reason for having three rods is the position of any object, such as this ball, can be specified using these three reference lines. This reference line points in the direction which we call up, which is a different direction here than it is on the other side of the Earth. And these two reference lines specify a plane, which we call horizontal or level. In this film, we're going to look at the motion of objects in this Earth frame of reference and in other frames of reference moving in different ways relative to the Earth frame. Well, let's look at a motion. This steel ball can be held up by the electromagnet. Now I'm going to open the switch and you watch the motion of the ball. The ball is accelerated straight down by gravity along a line parallel to this vertical reference line.
As you can see, the electromagnet is mounted on a cart that can move. And I'm going to do exactly the same experiment that Dr. Hume did, but this time, while the cart is moving at a constant velocity. The cart is pulled along by a string which is wound around this phonograph turntable, and that pulls it with a constant velocity. When the cart passes this line, the ball is released, as you can see. I'm going to start the cart down at the end of the table so that by the time it gets to this point, I can be sure it's moving with a constant velocity. Now, I want you to watch right here so that you will see the ball falling. I think you can see that the ball landed in exactly the same position that it did before when Dr. Hume did the experiment with the cart fixed. But this time, the ball could not have fallen straight down. Let me show you why. The ball was released at that point. If it had fallen straight down, because the cart moves on in the time that it takes to fall, it would have landed back here somewhere. But it didn't. Now I'm going to do the experiment again. This time, I'm going to let you watch the motion through a slow motion camera, which is fixed here. As the cart moves by, the ball will fall, and you can watch in the slow motion camera. I'll show you this again. This time, there'll be a line on the film so that you can see the path. I think that you can see that the path of the ball is a parabola. But all of this has been in a frame of reference fixed to the Earth. How would this motion look in a frame of reference which was moving along with the cart? Frame of reference like that. Well, so that you can see what it looks like, I'm going to fix this slow motion camera so that it moves with the cart. Like this. I'm going to do the experiment again. And incidentally, I'll start it, and then I'm going to stand here so that when the ball falls, you will have something which is fixed as a reference point. In the moving frame of reference, I think you could see that the path of the ball is a vertical straight line. It looks exactly the same as it did before when Dr. Hume did the experiment with the cart fixed. If we were moving along in this frame of reference and we couldn't see the surroundings, then we wouldn't be able to tell by this experiment that we were moving at a constant velocity. As a matter of fact, we wouldn't be able to tell by any experiment that we were moving at a constant velocity. I'm going to do the experiment once more. And this time, I'm not going to stand here behind the ball as it falls so that you won't have any fixed reference frame. As far as you're concerned, that time, the cart wasn't necessarily moving at all. That time, when you couldn't see the background, then I think perhaps it was harder for you to realize that you were in a moving frame of reference. The important thing to realize here is that all frames of reference moving at constant velocity with respect to one another are equivalent.
Dr. Ivy showed you what the motion of the ball that was released from the moving cart looked like in the Earth frame of reference and in the cart frame. The motion looked simpler from the cart. Now I want you to watch the motion of this white spot.
You're muted, Roger.
I know, I just noticed. Sorry. Yeah, so back again. So the video gets more complicated after that, but it introduces you to the basic idea of frame of reference. Things look different from different frames of reference. And Einstein's relativity, in large part, is dealing with what observers see from different frames of reference. So I'll get onto my slides now, if I can. Right. Yes, slides. So my slides are here. Thank you. So the question being raised is, does special relativity have a preferred frame? And a preferred frame would be where things look simpler for an observer. And of course, as I've presented in other talks, the people who say they believe in Einstein's relativity all have different opinions about things. And so a question like, does special relativity have a preferred frame? Some people that believe in Einstein's relativity will say, yes, it does have a preferred frame. And other people who believe in special relativity will say it doesn't have a preferred frame. And this is all contradictory, and hence showing that Einstein's relativity is a total mess of people saying different things. Hence why these are anti-relativity talks. So on to the first slide. Here we go. As dealt with in a previous anti-relativity talk, I showed that physicists who considered themselves mainstream did not agree to the solution of the twin paradox. And so now on to the issue of, does special relativity have a preferred frame? And the answer to that is yes and no. Some people will say yes, other people will say no. Those in the mainstream do not agree. Whether there is a preferred frame or not is one of the issues that makes the twin paradox confusing. If you look at this picture for the twin paradox, you've got the astronaut twin going off in a spaceship and then coming back to Earth many years later, and the twin that stayed on the Earth has aged more than the twin who was in the spaceship. Now, one of the issues is some of us who complain that it's not really aging that is being affected, rather it's just the clocks that are different. But then there's lots of things like that to argue about. But in this case, you would say, well, there isn't, it's not symmetrical. Both frames for the twins are not the same, and so there must be a preferred frame. But then you get on to people who believe in Einstein's relativity, and they're saying, no, that's not a preferred frame, which doesn't really make sense to us who believe in a preferred frame. So basically, the relativity principle really means there's no preferred frame. And this is what Wikipedia says. In physics, the principle of relativity is the requirement that the equations describing the laws of physics have the same form in all admissible frames of reference, i.e. that means there's no preferred frame. And Wikipedia goes on to explain about preferred frame. So this is Wikipedia again, and it says, in theoretical physics, a preferred frame or a privileged frame, a preferred frame goes under lots of different names like preferred, privileged, absolute, and so forth, is usually a special hypothetical frame of reference in which the laws of physics might appear to be identically different, simpler from those in other frames. And I've had the video to explain to you what frames are. In theories that apply the principle of relativity to inertial motion, physics is the same in all inertial frames and is even the same in all frames under the principle of general relativity. And i.e., my comment is, in relativity, there is no preferred frame. But, this is a good but, got this person who calls himself the hammock physicist, Jones Coleman, and he's saying there is a preferred frame. And he's pointing out that he's a physicist. What does he say? I'm a Dutchman currently living in, well, my eyesight's so bad, but you can read that. He's saying that he's a physicist. And people like that will argue that Einstein's relativity, which is special and general, is not really a relativity theory. In his little article here, he says, what's wrong with relativity? He's pointing out the term special relativity is probably the greatest misnomer in the history of science. And basically what it means is Einstein's relativity is called a relativity theory, but that is a misnomer. Really, it's not a relativity theory. So it's been misnamed. People are talking about relativity, but really Einstein's relativity is not about relativity. And that creates a vast amount of confusion. If you say relativity, if you go and buy Einstein's relativity, you don't mean relativity. So we have this split, those who believe in Einstein's relativity as first group, who though they believe it is a relativity theory, and we've got the other group of people who believe it's not a relativity theory. Those who believe it's a relativity theory believe there is no preferred frame. And those who believe it's not a relativity theory believed there is a preferred frame as part of Einstein's relativity. So we have this split in what people believe in is Einstein's relativity. Okay. Thus, to the question, does special relativity have a preferred frame? Some people will answer yes, and some people will answer no. And that's because they don't all believe the same thing. For me, that means it's not a properly defined theory if people can believe different theories or things under the term special relativity. Mainstream does not agree on many issues in relativity. There is a difference of opinion. And Einstein's relativity is built on numerous differences of opinion. It's a collection of different opinions. It's not a precisely defined theory. And that's what I say, and people argue otherwise. Some people say, yeah, it is a properly defined theory. And I say, but they're only believing their particular version of relativity. They might believe that relativity is a relativity theory, as opposed to the people that believe it is not a relativity theory. So they don't really recognize that what they're believing is different to what other people are believing. So Einstein's special relativity started in 1905. That means there's over 100 years of literature on relativity. Thus, it is a vast subject that has undergone numerous changes and reinterpretations. hence I'm not able to cover every issue. I've got to just concentrate on a few issues and point out the absurdities and the contradictions in that particular issue. And I can't deal with the vast subject as it is. For those that are pro-Einstein relativity versus those anti-Einstein relativity, those pros have been trying to give the false front that there is not a collection of different opinions and disagreements. In my view, those who are pro-Einstein relativity are not playing fair. And so let's go to another example of what a physicist says. Is this person? It's George Spoot III, and he's an American astrophysicist. He won the Nobel Prize. And in his Nobel Prize lecture, he says there is a preferred frame. He says, and we read it through, one problem to overcome was the strong prejudice of good scientists who learned the lesson of the Michelson-Morley experiment and special relativity that there was no preferred frames of reference. There was an education job to convince them that this did not violate special relativity, but did find a frame in which the expansion of the universe looked particularly simple. More modern efforts to find violations of special relativity look to this reference frame as the natural frame that would be special, so that perhaps the suspicions were not fully unfounded. We had to change the name to the new ether drift experiment and present careful arguments, as the title ether drift experiment was too reminiscent of the Michelson-Morley ether drift experiment. So basically what he's saying is there is a preferred frame, and he had to work around that problem of many scientists believing there wasn't a preferred frame. So he admits in his point of view that preferred frame exists, and that's in the context of Einstein's relativity, and also admits that not every physicist believes in a preferred frame. So it's presenting once again an example of the split of those who believe in preferred frame and those who don't. So, and once again, it's an admission that there's not agreement, that there is disagreement in what people believe in special relativity. So now let's consider the scientific process. So I'm looking at a comment. I don't understand that comment. Next one is, so this is the scientific method as an ongoing process, and we know it's all about going around in a circle. So first one, the top one is make observations, and you go down, following the arrow, you go to the next box, which is think of interesting questions, then down to the next box, formulate hypothesis, and then you go on to the next box, develop testable predictions, then on to the next box, gather data to test predictions, and then you've got a choice of directions. Either you go up, develop general theories, or you go to the right and refine or alter or reject hypothesis. Then you go back down into develop testable predictions again. So that is the scientific method as a sort of never-ending circle. So the important box is this one. There's the box we go into where you refine, alter, expand, or reject a hypothesis. Hypothesis is really a theory to be tested, and if you test a hypothesis and you think it's valid, then you're more confident in calling it a theory. So the idea with Einstein's relativity is you start off with the idea that of the relativity principle, which means there's no preferred frame. but when you get to this box and you decide you need a preferred frame, then you add it. Thus, the people doing experiments, those who do an experiment that does not need a preferred frame, they conclude the experiment agrees with special relativity. But those doing experiments where they need a preferred frame, they get to this box and then they add it. And they still come to the conclusion that the experiment agrees with special relativity. So whether an experiment has a preferred frame or not, the experimenters are concluding it agrees with special relativity. So hence you can see from this ongoing going around in circles with the scientific method, it's just making a mess of the conclusions that people come to. People can go around the circle and conclude there's no preferred frame, and they say that's special relativity, and they go around the circle and conclude the opposite. In my view, start with special relativity having no preferred frame, and when need arises, it gets added. But people split. There are those who are prepared to add the preferred frame when necessary, but there are also those who think no preferred frame and refuse to want to add the preferred frame when it becomes necessary. So people will then end up being split into different opinions. Relativity was not properly explained at its conception. And for those people who say there's no preferred frame, often they use an unstated preferred frame. They use a preferred frame, but they won't say that's what they're doing. So if we go back to Einstein in 1905 on his paper where he starts special relativity, Einstein has clocks in a preferred frame, and I'll put them aside translation problems. I've dealt with a lot of translation problems in Einstein's paper, and I'm putting aside that issue. People were just split in their opinions from reading Einstein's 1905 paper on special relativity. And so the paper says the following. If we assume that the result proved for a polygonal line is also valid for a continuous curved line, we arrive at this result. If one of two synchronous clocks at A is moved in a closed curve with constant velocity until it returns to A, the journey lasting t seconds, then by the clock which has remained at rest, the travel clock on its arrival at A will be that equation so many seconds slow. Thus we conclude that a balanced clock at the equator must go more slowly by very small amount than a precisely similar clock situated at one of the poles under otherwise identical conditions. So basically what he's doing here, he's using an unstated preferred frame. He stated the relativity principle at the beginning of his paper, and he doesn't use it when he gets to these clocks. He has these clocks having different rates. The one that's moved is not the same as doesn't have the same time as the clock that stayed still. So he's not used the relativity principle when he's dealt with the clocks. And this extends over to light speed. If light speed c in a preferred frame, then it won't be c in other frames. So he's abandoned the relativity principle for his clocks. So if you abandon it for his clocks, you might as well abandon it for the statement about light speed. Now, of course, what does he mean by light speed in his paper? I find very confusing. But just going by a simple statement of his light speed, it's supposed to be a constant. But if you abandon the principle of relativity then it's not going to be constant. So if we go to this site, we've got similar things being stated. And this site also points out that relativity is a misnomer. And it's pointing out there is such a thing as Newton absolute space and absolute time, and they're retained. And that means you have an absolute frame, and an absolute frame is another way of saying you've got a preferred frame. Thus, my conclusion is the following. There's a lot of confusion in Einstein's relativity, with people believing different things to what Einstein's relativity is. The confusion caused by relativity being a misnomer and the messy process of the scientific method is just one example of some of the confusions that have been generated. So looking at the history, what we have is 1919, Einstein's relativity theory, supposedly confirmed by Anderton, and that was the general relativity, which he came from 1915. And 1905, it was special relativity. So Einstein's relativity being confirmed in 1919, that meant you were accepting the general relativity part from 1915 and the special relativity part from 1905. But really, general relativity is an update of what was being said about special relativity in 1905. So Einstein's relativity, RT, which I might get down as, is just a theory that allows updates. And if allow updates, how far are those updates allowed? It results in the relativity literature giving us vast amounts of conflicting opinions as to what Einstein's relativity is. An example of the contradictions, some people will say there is a preferred frame, and some will say there isn't a preferred frame. And it's all because Einstein's relativity is an ongoing process where you keep updating it. And that's what Einstein gave us at the beginning. He didn't give us a complete theory in 1905. He only gave you a theory which he was going to update later. And what you got in 1915 with his general relativity, but still that's a theory that would need updating. So once you start updating a theory, it just goes on and on and on. And so that's basically, I think, the end of my little talk. Finished. Thank you. Let's get back. Are you there, Franklin? Hi.
All right. Thanks, Roger.
Okay.
Some people are asking whether you have like a website or something. Do you have a particular? I noticed that I put up a link for your papers, though.
Yeah.
Which can be found in ResearchGate.
Yeah.
So
I got a website called Einstein Conspiracy.
Einstein Conspiracy.
Yeah. I see what you got. You've got in history, you've got the mainstream point of view of history, and then you've got an alternative point of view of history. So, and the alternative view of history is called a conspiracy. So hence I called it conspiracy. So you've got the normal things said about Einstein, and then you've got other things said about Einstein. And so my concentration has been looking on the alternative things said about Einstein. And so I look at all the things that the mainstream wants to ignore about Einstein, such as there was a lady who was working for Einstein, and she said that she and Einstein went to see alien dead bodies, extraterrestrials. So I'm prepared to look at all the things that the mainstream people don't want to believe in. Hence my website being called Conspiracy, Einstein Conspiracy.
Is it called that? Because I just tried putting in EinsteinConspiracy.com and didn't come up with anything. Is it spelled?
.co.uk, www.einsteinconspiracy.co.uk.
Yeah, K.UK. Let's see here. Let's see if I can find that for you here. So this starts out with history of unified unitary theory. Is that it?
Yeah, because that's another thing they ignore. The mainstream people, they tend to ignore Einstein's investigations into unified field theory, and there was a lot of people looking into unified field theory.
So if people want to go check that out, they.
And I also got onto the fact that alternative history people say that it was probably really Einstein's first wife who did the theory and not Einstein, because she was studying physics with him at their equivalent of a university.
Yeah, I got a joke on that. You know what you call that?
Yeah.
You call that the theory of relatives.
That's it. That's why it's a theory of relatives. It's his wife wrote the theory and he just got the credit for it.
Yeah, the theory of relatives.
So then he's getting the credit for somebody else's work, and then he's got to try to explain it, and then he doesn't know what he's talking about.
So we have just some basic questions here. Yeah. What ideas of special relativity aren't agreed upon, though?
Yeah, you got people who say they believe in special relativity, but when I sort of interrogate them, will give different answers to what they believe. And I've given examples in my previous talks that you got somebody saying there's relativistic mass, and it used to be taught there was no relativistic mass. So people have got different opinions about special relativity, and most of the time the mainstream try to cover that up. They kind of pretend that there is no disagreement.
But I think probably most people who say they believe in special relativity are vehement about saying that there is no preferred frame, that there cannot be such a thing, and that if such a thing existed, then special relativity would be invalid.
That's well, the people who believe that special relativity has a preferred frame, it means they really believe in a totally different theory to the people who believe there's no preferred frame.
Well, see, that would be news to me, because I don't believe that anyone. Well, you had that quote by Smoot or whatever.
Yeah.
But generally speaking, I don't think that anyone who claims to support the mainstream version of special relativity would ever say that it has a preferred frame. So that's kind of news to me.
It's a minority point of view. The majority point of view is special relativity doesn't have a preferred frame. That's the majority, and that's what I understand as being what's taught to students. But there's also a minority point of view that think special relativity does have a preferred frame, and I think that Spook was pointing out that he believed in a preferred frame, but he was also admitting that many people didn't. So this is what part of all the mess is.
So that's a very foundational question, though. But what do you mean by a preferred frame?
Well, the relativity principle is basically with the frames of reference they're equivalent, and when you've got a preferred frame, then there's no relativity principle. You're not going by the relativity principle. If you've got two frames, then by the relativity principle they're both the same, and usually that means you're talking about two inertial frames. But if you're thinking that they're not equivalent, there is a preferred frame, then you're saying you're not believing in the relativity. So it's a big fundamental difference. It's the issue of relativity theory. If it's a relativity theory, then there's no preferred frame. But if relativity is a misnomer, then relativity theory is not obeying relativity and it has the preferred frame. So it's how things have been totally messed up in relativity.
Yeah, I think this has to do with the postulates, which is that the first one says that all the physics works the same in any frame. Although I'm
Relativity
kind of wondering, was that just too much of a generalization? I mean, they always show it in terms of, say, inertial physics, like going in with the cart and the ball.
Yeah.
But, does that extend to things like light and sound?
Exactly.
Or anything? I mean, it's easy to think that it might, but, to try and answer the question of what a preferred frame is, if you think about sound, sound has a preferred frame in that it moves within the air, and that air, which is stationary, forms a particular frame, which is different than any other moving frame. So if you're, I don't know, try to measure the speed of light on, say, a moving open train, you would get a different number than the number you would get if you were just standing on the earth where the air is stationary. So in that way, where the air is stationary would be a preferred frame.
Yeah.
And really, that's the only frame which you could say properly measure the speed of sound, right? I mean, you can imagine you having difficulty trying to measure the speed of sound in, say, like the moving train, depending on which way the train is moving.
Mm-hmm.
You might get different numbers. So
yeah.
But then again, like if you were on the inside of a train or inside of a car, then that itself would form another preferred frame, right? Even though it might be moving relative to the outside air. But any measurement you made inside your little bubble of a car, that would be the frame that you would be making the measurement at. So I think part of the problem is that when people think of a preferred frame, they think that, there's only got to be one preferred universal gravitational frame, right? And I don't think that's true.
Yeah, that's part of the problem that people, I think, you agree that they may think that way. But it's sort of like if you got two inertial frames, and then they go and buy the relativity principle, and they're saying there's no preferred frame. So you're treating those two inertial frames as being equivalent. But if you brought in a preferred frame, you would say one of those frames was better than the other frame.
Well, it looks like we got Nick raising his hand, so let's see what he's got to say here.
He's muted. You're muted, Nick. You're muted.
Okay.
I
got it. Thank you.
Okay.
I looked at it, it said unmute, so I thought it was unmuted, but I have to click unmute. I was quite busy, so I hadn't looked at the title for this presentation. So when I saw it this morning, I was quite taken back because I thought, what? My goodness, the fact that the special relativity has no preferred frame. It's so fundamental to relativity. And Roger has made that clear and allayed all my knee-jerk concerns. But it did remind me, I've debated physics professors, relativity professors for 50 years and more. And I've come across a number of things. As Roger says, unfortunately, there's lots of confusion even within academia as to what the meaning of special relativity is. But quite often, relativists see a problem in special relativity and try to address that problem. They take the first step to becoming a dissident or critical thinker. And two examples of that would be John Field, who worked at CERN, and he was concerned about relative simultaneity. He felt that that was a problem. So he modified special relativity so that now there was absolute relativity, simultaneity. But he remained a firm relativist, quotes, and just said, oh, the mainstream doesn't have the correct version of special relativity. And another person who had the same thinking was Franco Soleri, and he wrote a book, Weak Relativity, and it's just a minor modification of special relativity. Also, I had a few thoughts, I think, relevant to this discussion about a preferred frame. I think Einstein started off, and he was looking to explain velocity effects. And to do that, one of the simplest way to do that would be to get rid of all other forces so that you could just focus on it, and the math would come out the simplest that way. But it turns out, Wheeler and Thorne, and et cetera, who wrote Gravitation, wrote in their book that actually these velocity effects are independent of acceleration, except how acceleration affects velocity. So the key factor is not constant velocity at all, it's instantaneous velocity. So what would really be needed to just say go from thinking about fixed frames or inertial frames is to simply talk about inertial frames and change the equation so that they were integrals when you go from, say, 0 to half c, and the principle stays the same. So there were a number of misconceptions about the speciality of inertial frames, at least in this particular, for these phenomena. Having studied how Lorentz had his preferred frame, where the ether rest frame was the medium for light traveling and through it at a constant speed relative to the ether, Einstein took Lorentz's equations and Lorentz transformations and said they applied to each and every inertial frame. But what he did then was really take Lorentzian theory, where you did have a real single preferred frame, namely the ether rest frame, and make it so that each and every one of the infinite number of inertial frames saw the world in exactly the same way that Lorentzian theory saw it from the ether rest frame. So I wrote a paper about that, which incidentally was accepted by the Institute of Physics, saying that special relativity actually has an infinite number of single preferred frames, and that's what causes all of the paradoxes. I just want one side point. In looking at general relativity, the gravitational field equations really aren't relativistic. Even though the equivalence principle is used to try, which is false, tries to make it look like it, they certainly don't claim that if you're in a rocket ship on the Earth, that if you think you're just accelerating because you feel that gravitational pull, that's never been claimed to be an equally valid physical view, like in special relativity, where they claim every inertial frames view is equally valid physics. So it's clear that from a gravitational point of view, if you're on the Earth and you're looking at the Earth's gravitational field, you have a preferred frame.
Yeah.
So that's just a few comments. Very good, Roger. Thank you again.
Yeah. Thank you. Yeah, the education system for relativity is really messed up. They don't go into this issue of Lorentz theory versus Einstein's special relativity. The issue of general relativity might not be a relativity theory. They don't go into it. They just sort of...
Yeah, just one more comment. I looked in the comment and I saw that James Keane says, "What's wrong with updates?" Well, there's nothing wrong with updates. The problem is that this really isn't following the scientific method in relativity. It's just that the relativity principle and the lack of a preferred frame, that foundation was so wrong that it's not a case of they're really updating and changing things. As I gave in that first instance, people try to put Band-Aids on it and then try and stick to say this relativity principle and special relativity is okay. I mean, it's like trying to transform a pig into an elephant. I mean, you don't do that by little updates. Yeah. You have to go back and start again from a sound foundation. So that's a qualitatively different thing. We have nothing against updating theories, but if the theory is just down a dead end and just its foundations are wrong, then just updating it makes it more building a long tower. You're just building a leaning tower that eventually will fall over by its weight.
Yeah. So my point of view is the updates have not been clearly stated. They've done an update and it's not been clear that there's been an update. So if Spoot is right that there is a preferred frame, then that is contrary to what's being taught to most people. And so that update has been not made clear to people. So that's my complaint about it. They're just going around in circles on the scientific method, and they're not making it clear when they've been doing their updates. So you've got somebody doing an experiment, and that person might not be using the preferred frame, and then they conclude, oh, this is special relativity. And then somebody else does an experiment, goes around in circles, adds the preferred frame, and they still make the same conclusion that they've proven special relativity. So it's this going around in circles, making updates, and not saying that they've been making updates, which is making a terrible mess. Okay.
I can answer Andrew's question here.
Yeah, well, actually, we have.
It's addressed to Nick. So I'll answer it. John H. Field from CERN has written a number of papers, and I don't know if he's still alive. He is, or what was the expert in the area of atomic process clock slowing, and he, in effect, talking about half-lives. And he said that the ECI frame, totally independent of the findings for GPS, the ECI frame is the preferred frame for getting the best comparison of the data on half-life, particle half-life decay. So CERN data in that area claims there is a preferred frame.
So what was the name again? John what?
John H. Field.
John H. Field. So when I do a Google search on that.
Very famous for inventing the concept of the field. No, that's not true. No.
Yeah, well, that's not enough for me to look up a reference. Is there a paper or something or some other term I can?
I have some I can put into the chat, but it'll take me a little while to get all of the references.
Yes, but we do actually have Andrew in the green room here, and he is an actual CERN scientist. So let's see here, Andrew, can I bring you up here? And I'm actually very interested in what you have to say. I mean, you're probably
me too.
A mainstream guy who should know. So can you set us straight? Oh, wait a minute, he kind of disappeared there. So I don't know whether he accidentally put himself down or not.
Here's a very short half-life. So.
Yeah.
But you know, he is has another comment here saying that it's a simple calculation to show that the half-life. And I'm just looking for that half-life calculation can be done. But I'm still looking for a particular reference from John H. Fields. But okay, Andrew is back. Let's see. There you are, Andrew.
Hey, can you guys hear me?
Yeah, like I said, I'm very interested in what your opinions are because we really need to have more mainstream ideas here. So it's like, where are we going wrong? Or what's your opinion on what we're doing here?
I mean, at least for the claim that the ECI is a preferred frame is completely wrong. I mean, it would be bizarre to see a paper from anything in nuclear physics or particle physics where somebody is basing their calculations on where the center of the Earth is. I mean, that just doesn't exist. I've never seen a paper like that. I've never seen a calculation like that. You could do it, but it's not bringing anything to the table.
And make a comment. This was not claiming that all of physics was, but for this particular thing, clock retardation, that's what the data seems to be from, if he's still alive, the expert, or who used to be the expert in this area.
I mean, I think maybe one problem is that I feel like you guys smuggle in the usefulness of special relativity and don't really realize it, because you guys talk a lot about muons, and some muons in the atmosphere seem to be decaying different than muons in a lab setting. But you need special relativity to figure out that, hey, those two particles in the first place were muons, right? I mean, these detectors at CERN and everything, they're basically giant special relativity machines, right? They're giant detectors. Many of them are, they're basically made out of subdetectors. Each of those subdetectors can give you a little piece of information about a particle, right? Some of them can tell you what the particle ID is, so it can tell you if it was an electron versus a pion, or it could tell you what that particle's momentum is, or it could tell you what the energy is. And so, or you might be able to get one of those things, you might get 2 out of 3 of those things, you might get all 3 of those things out of, it depends on what particle it is and what kind of energy range it is. And then you're just using special relativity at CERN to piece together the things you don't know. And when you don't know 2 out of 3, say the mass of the particle and the energy, you piece those 2 together and you find out, oh, that matches up exactly to what the momentum was as recorded in the tracking detector part of my CERN apparatus. I mean, that's why I always think it's a good idea for you guys to maybe play with the data. CERN makes a lot of this data available, and it's just, when I have students or interns come and work for me, I don't really sit down and teach them relativity. I give them data and tell them to start processing it, and we can talk about what they're seeing or what they're understanding. So I mean, when you guys sit here for eons talking about thought experiments, that's a hard way of doing relativity. I mean, an easy way of doing relativity is to look at the data in the sense that we have, if you want to understand relativity, look at where we can do relativity easy, and that would be.
No, I would say that.
Let me just finish. Look at where we can do special relativity and where it applies the most, and that is in particle or nuclear physics. You can't take the first step in either of those fields because you're basically immediately accelerating things or decaying things at near the speed of light. And just to take a first step to understanding what a decay looks like, why is there, how much energy was released in that decay, you need special relativity. And then special relativity builds from there with quantum mechanics to understand the radiative processes, or what decays are allowed by certain phenomena, stuff like this.
Well, let me mention a number of people who disagree with you. John Wheeler, I forget Thorne's first name, and the people who wrote the book Gravitation is also
provide any references.
I can. I don't have them on hand to second that particular point.
Well, also, I don't really care about your name.
I'll give you. I'll get your email and I'll send you an unbelievable my alma mater, Harvard, at the Harvard Cambridge Particle Accelerator, the RANET, many years said that special relativity doesn't fit the data.
Now I did dig
also the one who does it at Stanford Linear Accelerator. He said I can point you to the quote.
This is similar to
the first thing we do is unteach special relativity.
But you couldn't name a single frame that does violate special relativity. I mean, I don't know. You can name.
Yes, we can. Yes, we can.
What frame violates special relativity?
All frames it depends. All frames that are not part of the preferred frame for the particular phenomena that you're looking at.
So what?
If it's gravitation,
and name a preferred frame for it, then. What's a preferred?
There are an infinite number that don't apply. That's why the man who knew the most about the data and GPS says it disproves special relativity. What you don't understand is that there is one. If you happen to be in the preferred frame, then the data will agree with special relativity, as I explained.
Frame right now.
No, you're way off.
How do I get into the preferred frame, and for what experiment would that be valid for?
Well, for clock retardation, it's the local gravitational field. For electromagnetics, it would be just whatever is the rest frame for the EM field.
The rest frame for an EM field?
Yeah, because physics isn't, a frame is an abstract mathematical construct. It's not your reference to some abstract concept. It's Einstein himself said it's the interaction. All physics is local. It's the interaction between two physical entities. And that's where Lorentz started. And then Einstein came in with all of talking about inertial frames and made it into abstract math. And
so your
fortunately,
at CERN, what was his preferred frame? And what experiment was that on?
Well, I did find this reference. So some Googling found a paper by John H. Field about Signac and Haffey-Keating. Now, I haven't read this paper, but it's interesting that it says the role of preferred frames for light propagation and time dilation in the region of a massive spherical gravitating body, where, according to general relativity, space-time curvature is described by Schwarzschild metric equation is discussed in the context of Signac effect and Haffey-Keating experiment.
So this sounds like it's talking about black holes.
No,
this is talking. I don't know. It's got the word frames in it.
It's talking about the Earth.
Yeah, the Earth would be a region of massive spherical gravitating body. Yeah, that would be the Earth.
Okay. And so then what is their preferred frame in this paper?
Well, that would be the Earth, a massive spherical gravitating body.
Yeah, but everybody agrees the Earth is an inertial reference frame.
Earth is not an inertial frame. It's approximately treated as an inertial frame.
Yeah, but why would you? So what are you exactly getting at this paper then?
Just that there is a reference by this guy, and he's talking about something about preferred frames. Like I said, I don't have.
Okay, so there's a reference by this guy. He's talking about something about preferred reference frame. And where are you going with this?
We're answering your question.
Yeah, we're providing you a reference.
Mean,
so there's a reference.
Have you ever seen anybody do a calculation with the ECI in particle or nuclear physics? Where's that reference? Why would somebody do that? That's
because it best meets the data.
What data?
Of half-life decay of particles at CERN.
But Nick, you do need to spend a moment to go find that so that we can go post that. So that, I mean, that's a perfectly valid thing to ask for. You know, I was only able to find, for example, this particular reference, but if it exists, you know, that's a perfectly valid thing to go look for, I would think. I found just something now in CERN here. Z decays to B quarks in Higgs boson mass.
Okay. My research was on D physics, or more specifically, heavy flavor physics.
So I don't know whether, you know, that would contain the details that.
I know it wouldn't contain the ECI, because I've done that physics before, and I've done those calculations.
Anyway, what we point out is that when physicists talk about things, they get very confused. So data is being misrepresented. So when you're talking about data, does it have a preferred frame in it or doesn't it? And these physicists, they don't seem to make it clear what they're talking about. And
well, I mean,
given examples of
you go onto some physicist blog's page and you just read off the blurb they wrote about themselves, but you don't dig any.
No, it's the way you talk about things. It's sort of like relativity principle has.
Yeah, but you could be misunderstanding it, or maybe they're a poor writer of their personal
blog.
You have to dig into what their claims are.
You're just over talking me. Can I finish, please? I mean, what I'm pointing out is it's a very bad communications going on from physicists if they're not explaining things properly. A relativity principle basically means there's no preferred frame. And with these papers, they seem to be using a preferred frame, but then they're still saying it agrees with special relativity. So they're just not talking about things properly.
I mean,
and I'll gave examples that
in physics, there's a lot of times there's a smart frame to choose, right? And it's similar in Galileo mechanics or Galilean relativity. So sometimes there's a frame to just choose because it cuts the number of variables down immediately.
Yeah, preferred frame. If you go for the simpler frame, then you're going for a preferred frame. The thing is, you're just trying to overtalk me.
Frame.
Andrew, you're just trying to overtalk me. As pointed out, there are people who are saying that Einstein's relativity is not really a relativity theory, and calling it a relativity theory is a misnomer. So you got people believing that, and then you've got other people believing Einstein's relativity is a relativity theory. So that is just a communications breakdown. You've got a difference of opinion as to what Einstein's relativity is. So you can write all the papers you like about the data, but you're not making it clear. It's just a communications breakdown. Are you talking about a relativity theory, or are you talking about something different? And it's just communications breakdown.
Well,
I mean, back to people like Lorentz, he's not talking about a relativity. He's talking about a preferred frame, which is an ether frame, and he's using Lorentz transformations. And if you're going to Einstein with Einstein's relativity, he's got the same equations, Lorentz transformations, but presumably they're not supposed to be interpreted from a preferred frame.
That's because
you're not letting me finish.
Built up special relativity from people previous to him, like Lorentz.
So
transformations are part of special
you're
relativity.
talking me.
I mean, your point is very superficial. It's just like I've read some people, or they seem confusing to me. I haven't dug any deeper. Like, okay, cool.
Well, who do I believe? Do I believe the people who say that Einstein's relativity is not a relativity theory?
And you should actually.
Or do I believe the people who say it is a relativity theory? mean, that's not superficial.
I mean, I don't take my physics advice from people's blogs or from
and
YouTube
literature
videos.
out there about
I think
Einstein's relativity.
That's a good place to start.
Sorry?
Yeah, one at a time, please. One at a time.
Yeah, don't just overtalk me. If you please start again. What were you saying?
I was saying I don't take my physics lessons from YouTube videos or from people's blogs.
Well, you can make up your own theory then, can't you? And pretend it's Einstein's relativity. I'm going by what people are saying about Einstein's relativity. And some people will say one thing, some people will say something else, and other people will say something else again. And it's just a confusing mess of what different people are saying. They're claiming different things as being Einstein's relativity. And that is a communications breakdown.
Yeah, but Andrew, you're a practical person. So we got the question here of, what is the speed of these particles being measured relative to? So on a practical standpoint, how do you deal with these issues?
Could you repeat that again?
The question is what is the speed of these particles being measured relative to? So in your practical experiments, how does frames of reference come into your business?
I mean, it's kind of like last time, right? You build a detector or you go to a facility, and also in some cases, like the detectors I was analyzing were, orbiting the moon or on Mars or up on the space station or whatever. Those would just be like what we'd call the laboratory frame. You have a detector, it can measure the mass or the energy or the velocity of a certain particle or certain subsets of particles, and it's just what that is what it is in that measurement. Now, what is that particle? Did that particle behave the way according to theory or according to the theory or the way I'm modeling it or the way I understand it? Those models and those theories are typically done in a center of mass reference frame. So in particle physics and nuclear physics, there's pretty much two. I mean, there's definitely more, but to first order in the simplest order, you're doing calculations, you're doing the simulations, you're doing the theory in a center of mass frame because that's the easiest frame. It just drops out a bunch of dummy useless coordinates in your system.
What is that center of mass frame? Can you explain that? Where do you get the center of mass frame?
It depends. Like if you were to easiest order, if you were colliding two electrons together, they both have the same mass, and so the center of mass would just be right in between them. That's not true if you're, say, colliding a proton with a stationary target, right? That center of mass could be moving. The same is true if you're colliding dissimilar nuclei like lead and protons.
Okay. So now we had some other questions for you, I think. But although you were saying that that it would be a simple calculation to calculate decays. Can you explain that more? What you meant there?
I don't know if that captured correctly what I was trying to say, but a simple way to understand special relativity is to look at data from CERN. They make the data available, and it's really just a jigsaw puzzle, right? You have these different detectors. You have a particle travel through multiple detectors, and each of those detectors can give you a little slice of information, potentially slice of information. Some of them can't tell you anything about that certain particle, and it's a good exercise to say, like a tracking detector can tell you stuff about the momentum or the ID of the particle. So if you know the mass of the particle via its ID and you know the momentum, then you can use special relativity to calculate the energy of that particle. And then you see, does that particle hit a calorimeter in my detector? And that calorimeter would tell you what that energy is. And those two should match. They should match pretty well. And that's just a simple exercise in special relativity. And that's petabytes of data hosted online and freely available. People can write simple code to do that. You can even do it in Excel.
So we got a specific question to you, which is that talking about Signac or Hafik heating, are you familiar with them? and it's said that they're not usually covered in undergraduate physics courses.
I've heard of them, but not to any certain, not to any kind of expertise. But I mean, also special relativity is nice too. I guess maybe this deals more with like the decay stuff because, we know things like a neutron can decay into an electron and proton, right? We know that because of special relativity. Like that's basically doing the exact same thing with the detectors I'm talking about. You put a detector near, a nuclear reactor, same kind of onion shape, where it can tell you tracking information, tell you calorific information, and then you see neutrons decaying into a proton electron. Except that that's not really true because we know that if we use special relativity to do those, we're missing energy. And so then, that leads us to say, well, it also, just doing simple conservation of energy and momentum and angular momentum, we know there's stuff missing in that kind of decay. So we know that, a proton cannot just be an electron, or a neutron cannot just be an electron and proton. And you can even guess by looking at how the things are decaying, their trajectories, that, if my neutron's here and my stuff's decaying over here, but the momentum's not conserving, then something's coming out on the other side. So you could put like they put scintillators and they started eventually measuring stuff, and that's how we discovered the neutrino. And that's how that's how special relativity gets to use for things like that. I mean, that was 80 years ago, and I'm still using similar detectors to this day at nuclear reactors to do similar things.
Yeah, well, certainly that sounds like what is known as a time dilation and
in that instance, it's not time dilation. It's just conserving momentum and energy. It's just naively saying, I'm using special relativity. I know where my neutrons are. I measure stuff over here. It's not conserving energy and momentum. My best guess is on the other side. I should start putting detectors.
Yeah, I think, well, part of the confusion, I think that we were getting to this in our last discussion as to what parts of special relativity, because I think like Harry would say that mathematically, as long as you stick in one, like the center of mass frame, that, everything works perfectly fine. And, the Lorentz factor is perfectly applicable, and all of that is totally correct. But I think maybe the dissidents are discussing something which is not directly related to that. It would be something to the effect that you are doing trying to measure your experiment in multiple frames and coming out with, I don't know, the same answers kind of things. So, in a practical standpoint, you would never do that. That would be ridiculous.
I mean, in some sense, yeah, it would be, because like if I am colliding two protons at a certain energy, that's gonna look what can happen in those is different than, say, colliding two protons in a different energy. And so so each of those labs would have their own separate frame. And that converting from what you measured in your lab reference frame to back to the center of mass frame, that lets you compare to the theory and the modeling. That also lets you compare to other experiments, right? Because I don't want to sit there and figure out how to convert from my frame to their frame and understand exactly all the kinematics that were going on in their experiment. Just have them convert from their lab experiment frame to the center of mass frame, because we all agree on that. Everything's basically the same in that. And then we can just, it's at that point, you're just comparing apples to apples then.
Yeah, well, I mean, that's an interesting, analogy. You have two different experimenters using two different setups in two different frames, and you're pointing out the difficulty of reconciling those two.
Yeah, I mean, I if somebody else is doing a particle physics experiment, I don't want to become an expert in their particle physics experiment and know every little caveat about it. So when they do a measurement, they need to convert it to the center of mass frame, and then I can look at their data really fast and say, like, okay, I agree with this or not. Like, I don't need to sit for weeks with them and understand, do our two results really match up?
Yeah,
I mean,
but in terms of analogy, it would be kind of like, I think like the dissidents perhaps are complaining about a situation like that, but them claiming that all the results have to be the same, because this is the whole question of, is every frame or like laboratory, I don't know, setup equally good and comparable to each other, such that if one
that's
laboratory
one way of doing it is if we all convert to the same frame at the end of the day.
With these two labs, they wouldn't be looking at the same particles. They sort of like one lab would be looking at one group of particles, another lab would be looking at another group of particles. What you're really talking about if you're dealing with relativity is you need a lab which is looking at the particles and another lab moving with the particles. So when the particles are moving at sublight speed, that's not going to really happen. You're just going to making a guess of what's happening in the other lab. All this talk about, do an experiment in that lab, do an experiment in that lab. Oh, you're not looking at the same thing.
I don't understand that.
Well, try again. Sorry, I start again. No, you got two labs. One lab looks at some particles, another lab looks at some other particles. They're not looking at the same particles.
Yeah, but we agree that like all protons are they have the same properties. There's not like the Roger proton and the Andy proton and the Franklin proton. They all behave the same physics.
You're looking at different protons, aren't you? So you're not looking at the same proton. If one lab was looking at a proton, the other lab was looking at the same proton, you could compare transformation between them. But you're not doing that.
We do this too because when we built the LHC, we don't just start colliding stuff at 14 TeV and start cranking out results there. We do start colliding stuff at 500 GeV, 1 TeV, because that's what some of the other collider complexes were at, and we see the exact same physics that they see, and that's one way of benchmarking. Okay, yeah, we have.
But you're not getting your CERN accelerator and then saying, right, I'm going to accelerate that at a sublight speed and see what happens.
Well, what would you expect happen?
Well, that's relativity. You've got two frames of reference. What happens in two different frames of reference?
You can do the calculations in the rest frame of the particle. That's basically.
But you've not done the experiment. You're not done the experiment. You're comparing. If you want to compare two frames of reference, you've got to have the apparatus in both frames.
So
frames.
That's your checkmate for relativity.
And you're not doing that. So you are taking a preferred frame. You're taking the lab frame as the preferred frame.
Well, the lab frame is not a constant frame. That's not a preferred frame.
You're approximating it to it. The Earth is moving. The
lab frame is not relative.
It's not an inertial frame, but you've got to pretend or approximate it as to be an inertial frame.
Well, lab frame could be the preferred frame if you're inside the accelerator. The dominant frame is going to be the electromagnetic field.
What I'm asking is, if you're in the rest frame of a particle, what do you expect to be different there? Because you can do the calculations and you see that, okay, the particle behaves this way, and then when I do the transformation to my lab frame, relativity tells me exactly what I measured then.
Well, if you're in the lab frame and you're watching the particle moving, right, and so you're saying, right, that clock on that particle has to be at a different rate to my clock because it's going to decay at a different rate. But if you're in the frame where you're treating that particle at rest, are you going to say that it's the other way around? Are you going to say, oh, it's the clock in the lab which is slower, or are you going to say the clock in the lab is faster? And you haven't done that experiment.
Oh, I mean, we have. We've taken very cold neutrons and very hot, very high energy neutrons, and we've looked at the decays, and the decays change exactly with what we expect with special relativity.
You haven't done the experiment.
We've actually taken neutrons from the same source and put them in like.
You haven't done the experiment. I've seen no write-up of it. There's nothing saying that when I'm in the frame of going with this particle, it's going at sublight speed, and I'm treating it as rest, and I can look from that frame and see the clock in the lab frame and say whether it's faster or slower. You've done no experiment like that.
The faster a particle goes, the longer it takes to decay. Like that's
right. But what you have not looked at is what you call a fast particle. According to special relativity, the particle at rest in the lab frame is going at very high speed in the particles frame. So it should be the one. It should be the one that's decaying slower.
No, because the particle that I took at rest or very cold and accelerated to high energies, that underwent acceleration. Like,
but you're only looking at it from one frame. The difference between Lorentzian theory or any preferred frame theory is that there is a single preferred frame. That's the model, and special relativity.
This is.
Are you talking? The special relativity only makes sense if you're saying these are just observed effects. Because if I was in the accelerated proton, I would see the rest particles slowing down.
Emission accelerated, so it has a different space-time interval than the one that stayed at rest. So I can't equivocate them.
No, that doesn't answer the question. From the, let's call the particle at rest in the lab A, and the particle that's going near the speed of light relative to the
had to accelerate.
No, I'm just talking about two different particles, A and B. Okay. A is at rest in the lab frame, and B is going at extremely high speed in the lab frame. In the lab frame.
From how'd you get it to go?
Let's say it came in that way and just it happened that way.
Okay, so like a non-physical system.
Okay, now special.
It just existed.
But that's what you're doing is making a non-physical theory, because special relativity says that predicts that in B's frame, it's A who's
only
going
if
slower.
What you did in that just magically became instantaneously near the speed of light.
I don't even have to do that. I'm trying to get by the blinders you have on.
Well, I mean, why would I think
special relativity says all frames, the inverse transform from all frames is symmetric. So whatever you say, from whatever you're saying when you look at the data from the lab frame, if you had looked at that same data from the V frame, it would say the opposite, that it was.
No, because in this exactly in the scenario I've said, you would have to accelerate it. So I don't know why to equivocate them.
Yeah, but.
Like I'm talking about the system. Like at CERN, we use basically just hydrogen bottles. Those hydrogen in those bottles are, in the ECI frame, let's say, and then when I put them in the Large Hadron Collider, I have to accelerate them to get there. So if I wanted to equivocate,
in your explanation, then the ECI frame becomes the preferred frame, because for everything that's accelerated relative to the ECI frame, you can't use special relativity.
No, because first of all, the ECI frame isn't something I would use in that scenario, but also because they're not equivalent. Like if you want to equivocate two and say that these two experience the same time dilation, they have to have the same space-time trajectory. Like if you can't establish that, why would I assume that then? I'm sorry. Like, give me an experimental scenario where I can establish that, and then I might give you some veracity.
The relativity principle is
I know it's
really
hard, Nick. Yeah, I know.
No, God,
It's hard.
Andrew,
Physics
what's
is
hard
hard.
is talking to
Experiments
you.
are hard.
So get back to the words. The
I mean,
relativity
yeah,
principle
you can huff and puff all
is
you want, but you
there
got
is
to
no
think of
preferred
these as
frame.
realistic
So
systems where I set up an experiment and do the experiment, and how
Well,
does that actually correlate
you're
to the theory?
you're saying things that are anti-special relativity.
Like
If you
what?
can't use special relativity and its equations, if you had acceleration in the past, then special relativity is of no value. I mean, all these things that we've been through.
I mean, once again, are we talking about the equations of special relativity, which I think everyone could agree generally hold true for any particular frame of reference? Or are we talking, like I said, what the dissidents are complaining about, which is the use declaring all of those frames as being valid simultaneously, which is the thing that, I don't know, most dissidents seem to be claiming.
That's right. That's what the theory said.
But that's apparently, you can find people in the mainstream saying that yes, they're all valid, but this, I don't know. So we're complaining about that being apparently.
Special relativity is also a useful tool, because if you find something that violates special relativity in a certain frame, you know that
the preferred
can't
frame
be allowed in a different frame. So like if I know, I know a neutron can't decay into uranium, that would violate a decay mode just because of special relativity in that neutron's rest frame, let's say. So I know to not. So I know if I ever saw a neutron in whatever frame decay into uranium, that would be a good test to violate special relativity.
All right, let me give you two examples to think about. You don't have to, just do an ad hoc response. Ron Hatch, who was one of the key engineers at GPS, went to NASA, and the NASA people there said they were using special relativity, but he pointed out to them that they were using in interplanetary space the solar barycentric frame, the center of mass frame. And in that frame, you got the right answer because that was representing a preferred frame. If you use other frames, you would get the wrong answer. So they had to get to the right answer. And the best approximation of that was the solar barycentric frame. Okay. So that's one thing. They looked at the data. They thought they were using relativity's equations. They were convinced they were using special relativity, but they were using a preferred frame. Now, so the problem with special relativity was that it basically was observer-centric. It said that all inertial observers have equally valid views. The problem at NASA was that the engineers were data centric. In other words, hey, the data agree with the equation I'm using, but they didn't have in their mind a coherent physical model, and they never went beyond looking at it from the non-preferred frame point of view. And the other aspect is from Einstein himself. He says all physics is local. It's not. So you have to, if you have a coherent physics model, you're saying it's motion with respect to at least two physical entities. Okay? Not if two things collide, okay, it's not with respect to Uranus's preferred frame or Saturn's or whatever. It's that's what's happening physically.
I mean, I used to work at NASA. I was at NASA for 4 years, and I did radiation physics there. And I looked more specifically. I looked at neutron physics, neutron production in space, and that included designing, engineering, tech demoing, a couple of neutron detectors while I was at NASA. So that was all done on Earth, figuring out how neutrons interacted with those detectors, and then flying them on one satellite was going around. Well, that flew before I joined, but I did look at that data from when I flew to the space station on Artemis 1, and then some neutron data from Curiosity. And they all agree, and they all agree with special relativity. And you use special relativity to calibrate those detectors, right? Because part of that calibration is looking at how neutrons.
Hold on. When they say it agrees with special relativity, do they believe special relativity is a relativity theory, or do they believe it's not a relativity theory?
I don't know what that means.
But,
Special relativity.
But Andrew, you gave an example. You went back to exactly the mindset you had before, as if nothing I said had any impact whatsoever.
I mean, because
you said, all right, here's the data. I use this equation. They agree. Oh, therefore, place closed.
I mean, because you're talking about somebody that had a conversation with somebody else, and they said they weren't. NASA told them what? Like, okay, that's a cool story. What am I supposed to do with that?
Nothing, Andrew. You keep yours, and let's move on, Franklin.
No.
Well, I have been digging up. So you pasted 3 references, Nick, into.
And a fourth, actually, below.
I looked at the first reference. I don't see the center of Earth ECI frame in that in any equation in that one.
Yeah, I would admit I'm not seeing that myself either. Yeah. I mean, they're talking about the relativistic calculations, but I'm not seeing. Of course, these papers are rather long. This last one is pretty long here, but certainly in the abstract, it's not mentioning anything about any preferred frame that I can see. So, I mean, we got to be careful about that because I do encounter this. Yeah, this last paper.
You asked me on an ad hoc thing about one particular point. Locate the exact thing. Here's what I had from John Field, and Andrew wasn't expected, but I was in continual communication with John Field, and he said, this is the conclusion. I use a preferred frame, the ECI frame, when I'm looking at the data or trying to predict the data in CERN. It's the preferred frame.
Although perhaps maybe he was bright enough not to ever actually admit that in public.
Well, I don't know. Look at the last one I had. It's number 16 is in brackets, and the very last one.
You posted that in the private chat here? Or?
Yes, the final one in private chat.
Let's see here. I'm not seeing that.
So I say that there are a lot of people who are saying they believe in special relativity, but they don't believe it's a relativity theory.
I don't know what that means.
Well, the relativity principle, they're not using the relativity principle. If you got the relativity principle, then A and B, you got 2 observers in different reference frames, A and B, and then it's symmetrical. If A says B's clock is slower, then B will say A's clock is slower, and that's symmetrical, and that's obeying the relativity principle. But if you're saying that A says B's clock is slower and B says A's clock is faster, that is breaking the relativity principle, and you're using a preferred frame. So you've got all these people who are believing if A says B's clock is slower, then B says A's clock is faster. You've got everybody not believing in relativity, but they're still calling it relativity.
Yeah,
and
except it seems like that's
the whole basis of the problem.
System.
It should not be called relativity. It should be called something different. It's not a relativity theory. If you're thinking a relativity theory, then you're believing A has a slower clock and B has a slower clock, which is wrong.
Relativity is relativity, for physical systems. Let me make that caveat. It has to be a system that
you're
can
making
exist
up.
in reality.
Hold on.
What?
You're making up stuff. I've
Yeah.
gone through the literature. I've gone through what's being taught, and they're not saying what you're saying. Where you're making all your stuff up from, you're just moving the goalposts again. It's the scientific process is to just keep going around and around in circles, making updates. You making up the updates the way you want them, and somebody else has gone a different way with their updates.
Yeah,
Well,
but
I
the
mean,
actor has to do this in a practical standpoint. Like an engineer who builds a bridge, he actually has to get results. Otherwise, the bridge falls down, right? So,
well, it does happen. Engineers put a bridge up, and sometimes it falls down, and that's communication breakdown. And you've got the same thing with physicists. They've got a communication breakdown. They're
similar to
talking
that,
stuff,
the
and
person that
they're
only
not
draws
agreeing.
bridges
It's a
on a piece of
communications
paper
breakdown.
won't have a bridge stand up in reality.
Okay, Andrew, I have a question for you. What's the physical meaning of special relativity's time dilation equation?
What do you mean by physical meaning?
Oh, that's revealing. What does it mean physically? All right, I'll give you two choices. It means I'm in frame A, and I'm looking at frame B moving at velocity x. What does special relativity's time dilation equation say about what's happening in B, in frame B? Is his clock physically slowing down, or is it a just observed effect?
So his clock. Wait, what do you mean physically?
Okay, we have A and B. B is moving with velocity v with respect to A. Is special relativity saying that B's clock is physically moving slower, accumulating proper time slower than A's clock?
You haven't really defined a reference frame.
I find A and B. I have two different frames, A and B. And they're moving at relative velocity v.
Okay.
Can
they
I add on this?
In principle, they could be both time dilated from what I'm.
Right, they're both time dilated. So does that mean that they're both running slower with respect to each other, or is it saying that they're just observing the other clock to be running slower?
They would both be running slower.
Okay, thank you. So that's it.
There's disagreement on that. There's some people saying it's just an illusion of observing the other clock slower, and some people say, yeah, it is actually going slower. So there's disagreement on those sort of issues as well. But getting back to the preferred frame, a preferred frame means you're not using the relativity principle, and which means when you've called it a relativity theory, that's a misnomer. And people are treating relativity theory as a misnomer. It's been a theory that's been given the wrong name, and they're treating it as a preferred frame theory, even if it's unstated preferred frame. And that's the whole problem.
What would be an example?
You've got all the words confused. It's communications breakdown. If you're an engineer who's building a bridge,
of a preferred frame in like a nuclear, what would be an example of a preferred frame in a nuclear?
I gave you the example. Right. A frame and a B frame. A frame says B's clock is slower. B then says A's clock is faster. And that means the A frame is a preferred frame. But if it was not a preferred frame, you would be saying A clock is slower and B clock is slower. And that's the difference. Are you going by the relativity principle or not? And most people, I think, are going by the preferred frame. They're not using the relativity principle, and hence it's not a relativity theory.
I mean, Andrew uses the center of mass frame. So,
yeah,
would you claim that he's not
relative? If we go back to Einstein's paper in 1905, there's nothing about using the center of mass frame. So it's just another add-on. It's that the scientific method of going around in circles all the time. Somebody's adding this something about center of mass. Well, where's that in Einstein's 1905?
Well, I mean,
it's
you're
not there.
acting like Einstein came up with like Einstein came down from the mountain with tablets of that read.
We didn't do that.
Is.
I'm pointing out Einstein didn't do that. He said some things.
Relativity is a theory of science.
Can I talk, please?
No,
Einstein.
Everything you're saying, that criticism of special relativity is exactly true for everything else in science.
No, it's not. Can I talk?
People are still working on and developing classical mechanics, classical E&M. Yes.
Can you let me talk, please? So Einstein did not come down from the mountains like Moses and give the absolute law of what his theory was. He didn't do that. He didn't give the absolute theory of what he thought things were. He said things in 1905, and they called that special relativity. He said other things in 15, they called relativity. And between then and then, he was making changes. He was changing things around, and he's adding things. Minkowski's space-time was not in the 1905 paper of special relativity. That's something else that was added. So it was something that was changing all the time. It's the scientific process of going around in circles all the time and adding things to it all the time. So it's not there. So Einstein didn't say lots of things, and it's all been added later.
That what field of physics do you think is not being actively developed or worked on?
But that's kind of beside the point.
Yeah, I think we were talking about relativity. If you want to talk about Darwin's theory, of course, yeah, you look at Darwin's theory.
But the same is true
about DNA and other things. But sort of like it's been clearly explained what's been going on with Einstein's relativity. It's not being clearly explained. People are ending up believing that Einstein's relativity is a relativity theory, and other people were ending up believing it's not a relativity theory. And what's the problem? It's communication breakdown. People are looking at it and coming to different conclusions as to what it's mean, and nobody's making it clear what the updates are.
Well, I mean, I don't know what to say because, special relativity is a theory of science. It's something that's actively developed on, and that's true of all of physics.
But it's not a relativity theory anymore. Most people are not the people like Stu are not treating it as a relativity theory. But when they're teaching it, they're telling kids it's a relativity theory, and they're completely confusing them.
Yeah, I mean, this is just kind of your qualm with, they should come up with a new name for special relativity.
Yeah, it should be called something different. When Einstein was first told it was going to be called relativity, he disagreed with it being called that. He thought it was a theory about invariance. And that's not emphasized.
The exact same is true for
the theory. The theory's been given the wrong name, and it's leading people to think the wrong thing about what it's about. It's total confusion.
The exact same thing is true of classical mechanics. People say classical mechanics, and they almost always only mean Newtonian mechanics, force equals mass times acceleration.
Most of the time, I mean Newtonian physics when I say classical mechanics.
Yeah. But if you learn classical mechanics,
Einstein's relativity and Newton's theory, and then quantum physics is supposed to be not classical mechanics, and so that's another area of confusion. But at the moment, the area of confusion we're dealing with is Einstein's relativity, in particular, the problem about a preferred frame. It's not a relativity theory. Einstein's relativity is not a relativity theory. If they admitted to that, then a lot of the confusion would go away. But no, they're not admitting that. They keep calling it a relativity theory. And so they're misnaming it.
Why don't you have this problem with classical mechanics?
No. When you read papers on classical mechanics, they're going to make it clear what do they mean by classical mechanics. Do they mean both Einstein's theory and Newton's theory, or are they just meaning Newton's theory?
No.
And by the way, Andrew,
classical mechanics is not Newton's theory. In fact, if you learned anything about classical mechanics,
okay, Andrew, you're going off on a tangent here. Andrew,
I disagree, Andrew.
I let
Newtonian physics has been built on
What we're saying, Andrew,
if you have a
is
problem
that
with relativity for that, you're going to have the exact same problem with classical mechanics because
no,
there's no problem with
Andrew. We're saying that the fundamental foundation of special relativity is flawed.
You can't use
Can you
Newtonian
mute them,
mechanics
Frank?
to
And they're just
explain
going to talk
even
over
the
each other.
basics of like
Can you mute them?
stellar mechanics.
Can you mute them? Franklin.
Newtonian mechanics fails after the three-body problem. It fails after the double pendulum. It fails after coupled oscillators or damped-driven oscillators. Right?
Disagree.
If you want to learn just
I disagree. I disagree. Newtonian mechanics and it's clear what the changes are. It's
very
clear
fast.
what the changes are in Newtonian
Andrew,
physics.
You set up a straw man. We had never said that. We made it clear that the point the foundation of special relativity is so flawed that no fiddling with it can fix it. You either have to restart from something else.
Now, look, guys,
that's at the opposite end of the spectrum.
Let me break in here for a second because this is not a presidential debate. You guys need to stop so that we can hear what the other person is saying, because in the last minute, I don't think anyone can understand what anyone was saying. So with that caveat, carry on. But
okay, so Andrew was just trying to cause a diversion there, because it's kind of like, oh, you're having problems explaining Einstein's relativity, so you want to go on. You're doing it again.
Einstein.
You're talking again over me. I'm talking and you're trying to talk over me again. So I can't follow what you're saying if you're going to talk over me. Now I'm pointing out you're trying to set up a diversion. Einstein's relativity is probably not a relativity theory, and that's not been clearly explained anywhere. They're leaving people to think it's a relativity theory, and when other people are thinking it's not a relativity theory. All the updates to Einstein's relativity are not being clearly explained.
So is that just a nit? I mean, I think that's Andrew's point. It's like,
no, it wasn't Andrew's.
It's like, so what? It's like, I don't use that part of relativity.
Like
he was avoiding that.
I mean, I don't hold Einstein in any magical, special, elevated position. I use special relativity. I've read Einstein's initial papers on them. I think they're fine. All right. I think they established the roots of special relativity well enough. And special relativity has been developed a bit since then. It's still used today. So, I mean, if you think it's a mess, I would say go back to that root of special relativity. Go back to those papers and look at the data from CERN, because it's very easy putting together the data from CERN and exactly what Einstein's saying in terms of like E equals mc squared. What is the relativistic momentum of a system? What is the relativistic mass of a system?
Can I come in?
Put all of those things together with simple data and simple experiments.
Can I come in? Right. No, it's not clear from Einstein. What you got, he said certain things, and then the physics establishment decided to believe something else instead. If you go back to Einstein, he's made omitted changes, and people will say, yeah, he's made mistakes in relativity. Sort of the main issues being the cosmological constant. He first of all introduced it, and then he thought, well, I should take it away again. And then people were saying, yeah, bring it back again. So it's admitted that there are changes being made to Einstein's relativity, but he's still saying a lot of things, and people have changed it and have done something else, and they've gone into no explanation why they've changed things from what Einstein was originally saying. They've just changed it, and you go, well, what proof have they done? What proof have they done to prove that they shouldn't go by what Einstein said? One of the things is that Einstein has said is he didn't believe that there would be such things as black holes, and that's one interpretation. When he's talking about an object collapsing into under its own gravity so that light doesn't escape for it, that's what we now call a black hole. He didn't think such a thing would exist, but then people come along and said, well, black holes exist, Einstein is right. But what they really mean, they believe Einstein's relativity is right, even though they don't believe what Einstein said about Einstein's relativity. So they've made a change there. Then they've done numerous changes like that. They're going by Einstein's relativity, and they're saying, "Oh, it's right," but they're not going by what Einstein said about it. They've just changed it, and they've not explained why or how they've done that. And it's going around in this scientific process of keep continually going around in circles, making changes, and then they've not admitted to what the changes are, and that's relativity for you, just a complete mess of changes.
Okay, that's I think a good summary. We are getting towards the top of the hour. Nick, you want to put in a last word here?
Yeah, I just want to have people remember what Andrew and I were talking about when we were talking about the rate of clocks in frames A and B, and what was the meaning of time dilation. And Andrew said that clock A was going slower than clock B, and clock B was going slower than clock A. And by going slower, meaning simply accumulating proper time, which is well defined, an absolute, very good physics concept. They were both going slower than each other. But just remember that we don't have to debate and think about that.
Yeah. Well, my rebuttal would be, how do you know that system's physical?
I mean, the real experiments show that that never happens. Is that clock A and clock B, one of them is slower than the other, so it just doesn't happen.
A lot of things are not physical. A lot of things come from Einstein's thought experiments, and these thought experiments are given things like the twin paradox and so forth. So they're doing experiments that are unphysical. Einstein's experiments most of the time are unphysical. Or he thinks about what happens if you sit on a beam of light and want to look into a mirror. Do you see your face? It's an unphysical experiment. Nobody's going to be able to do that. Well, not so far. And so it's thought experiments which you can't actually do. So most of it is unphysical. Most of the statements from relativity are unphysical statements.
Well, when Einstein came up with that, he didn't have access to radiation and particle collider. But all those things did come.
So he was thinking of things which you couldn't do experiments for.
Yeah, but I mean, like, when he was shown the calculations using special relativity about making nuclear reactors and nuclear bombs, he immediately understood what the implications were. I mean, he was a theoretician.
If you do the E equals MC squared,
none of this technology existed.
If I do a talk on E equals MC squared, then most of the things said about that are false as well from what we're teaching students. That's just all false. I mean, the E equals MC squared was before Einstein came along. And so, like, people were coming up with equations similar to that from Newtonian physics before even Einstein's relativity turned up.
You can't actually
that is
an equation that's
again. It's another diversion.
Like, in thermodynamics, that's true. It comes from the binding energy of a gas.
Yeah,
Einstein extended it to the binding energy of matter.
I don't think he said it.
Again, it's Einstein. It wasn't some he wasn't some Moses character. He was building up on people before him. That's fine.
So he didn't reference what he was building from. That's another problem with Einstein. He didn't reference what he was building from. So he didn't give citations, references. He didn't say, "Oh yeah, somebody else has come up with this time dilation thing."
And he actually, I think his 1905 paper, his first paragraph, is mostly praising.
I think he
people
mentions
like
Maxwell, Lorentz, but he doesn't cite papers. There's no references. He's talking about an experiment about moving a magnet, I think, and he doesn't give a reference for that. Who's the experiment's doing? Is he talking about? He doesn't say. He doesn't talk about the Michelson-Morley experiment. He doesn't talk about Galilean transformations. He doesn't say whether his theory is not part of Newtonian physics. There's lots of things he does not say. He does not say whether he got the principle of relativity from Poincaré, who mentioned it earlier. He doesn't say what he's working from. It is just a complete mess of a paper.
I mean, like, when I write a paper, I don't reference everything. There's
Well, he didn't
there's
reference
a
anything.
reasonable
He
amount of
didn't
references.
reference anything. There was no references of what papers he was going by.
Yes. Well, we've reached the top of the hour here.
So we got to go now. Okay. Thank you.
We've reached the top of the hour here, but I don't know whether we have really answered this question. Does special relativity have a preferred frame?
Yeah.
So maybe just go around and just answer: does special relativity have a preferred frame? Yes or no? I would say yes. My particular own answer to that is that if the postulate says that light travels independently of the emitter and the receiver, the only way that can possibly happen is if there is a preferred third frame at which it's traveling at a definite speed. So I would say that it does. So I vote yes. I mean, what do you think, Andrew? Does relativity have a preferred frame, or do you care?
I say they had it. I say they had
it doesn't. And I guess from Nick's point, when he says something, maybe he could point out to which paper he thinks is the best one that shows a preferred frame, and I'll try to give that a glander before whenever this happens again.
Okay.
And Nick,
no, it definitely doesn't. I think Franklin's logic is 100% correct, but unfortunately, all of the derivation is based on there being an infinite number of preferred frames.
So is it yes or no?
An infinite number of preferred frames is a contradiction.
So
a preferred frame is just a single preferred frame. And when I talk about a preferred frame, I'm talking like local preferred frames, because I'm talking about a physical model.
Okay, Roger, I'm going to give you the last say. Okay, go ahead.
I think that's another. Thank you. That's another diversion. I do a talk where I deal with the mathematics that Einstein deals with, and it doesn't make any sense. So it's another issue. He's saying things which don't make any sense, and then he's doing mathematics. It doesn't make any sense as well. So I can't deal with all this in my talk. So basically, for this talk, I'm pointing out there's people who believe that calling it relativity theory is a misnomer, and really it's not a relativity theory, but that is a communication problem for people believing different things as to what relativity is. Next week, deal with the mathematics being a mess. Thank you.
All right, it sounds like it was 1 vote yes, 1 vote no, and 2 votes all of the above.
Okay, thank you. Well then.
All right. Well, thank you for joining. I especially thank Andrew for joining us
to
help represent the mainstream. We really need more people like you in our group. All right. So, but that will do it for this episode.
Bye then. Thank you. Goodbye.